Welcome, welcome, welcome to Miss Lisa's Science and Math. Today we're talking about physics. We're going to be talking about physics in this book. Velocity is what we were talking about. So welcome, join us. This class is designed primarily for homeschoolers, but if you like the way I explain stuff, come on in and we'll talk about velocity. Now, what is velocity? Good question. Velocity is speed plus direction. So if I say I'm going 55 miles an hour, that's the speed. If I say I'm going 55 miles an hour northeast, that's the velocity. Hold on, I got water. And I bounced the camera. Sorry about that. Now, this physics book, and also the physics book at the high school where I teach, use this idea, and different physics books do this a little bit different, but it uses the whole idea of reference point. So imagine you're on a football field and you start at the middle of the football field. If you go to the right, you could call that going positive. And then if you went back the other way toward the left, you could call that going negative. You can consider your distances that you go positive and negative in regard to a reference object. And then that would make it, instead of a speed, you could call it a velocity. So that's the thinking they have. Another physics book I used to teach out of a long time ago, decades ago, and we will not talk about how many, it only considered a velocity if you said northeast, or like a compass measurement where you're saying you're going, like with latitude and longitude, and you say you're going 14 degrees, north of east. They would say that book, the old book, said that's a velocity. This new book pretty much uses velocity instead of speed. And because they considered any speed to have a direction, because you could say you're going in a positive direction or a negative direction. You could be going forward or back from the way you went. So in this class, we will use velocity the way they do with this book. But if you're watching this video and you're doing a different book and you have a different teacher, they might have it the old way, the way that my old physics book that I used to teach out of had it. So most of the new physics books seem to have this whole idea where they pretty much use velocity, where they're giving a speed is distance over time. And they will call it velocity instead because it's not a negative distance. And in reality, distances can never be negative. Distance is always positive. I say it's 2 miles from my house to the library. It's 2 miles from the library to my house. It's not negative 2 miles from the library to my house. But they would call it, they would say in reference to the library, it is negative 2 miles. But in reality, we don't say negative 2 miles. Distances are always positive. So when you do the distance formula in math, it's the absolute value. So if none of that made sense to you, don't worry about it. It's just that there's a different ways of looking at these problems. But it really won't matter once we're doing the problems. Okay, hopefully that kind of makes sense. All right, so your book starts with this picture, and I'm going to show it to y'all. It is a lady running, and this lady is from Atlanta. She's from right here where we are, and I used to teach her niece. She was in my physical science class. This is a very famous athlete. Her name is Florence Griffith Joyner, but they called her FloJo for short. And I taught FloJo's niece, and FloJo's niece was so proud of her aunt being an Olympian and being famous. She was so famous. She was known for her flamboyant style. She had long, painted, fancy fingernails. She'd run with her hair down and so pretty as she was running. So it's kind of fun. But she passed away. She died kind of young. It was sad. But you can look up her story. And I used to teach her niece. And she was real sweet. Her niece was a sweet girl. So anyway, we are proud of her, though, in this area, that she has connections to Atlanta. And, of course, her speed was, or velocity was very fast. So look in your book, and let's talk about two different ideas. One is vector, and the other one is scalar. In physics, if something is vector, then it has magnitude and direction. If something is scalar, it just has magnitude. So something that would be considered vector is position. It can have direction, velocity, displacement. Something that is scalar is something that has no direction. So Fahrenheit degrees, you don't say that there's temperature in a certain direction. It's, hot to the right or something like that. So distance and speed are both considered scalar. Scalar things don't have direction, vector things do. And in physics, we represent vector things with arrows because arrows show direction. So the difference in speed and velocity is velocity has direction. Now, so speed is S, velocity is V, and it's written sort of as a curve VV. Okay, so now we can get the average speed or the average velocity. We take our total distance divided by total time. Like, for example, if you were going to grandma's house and you want to know that it normally takes you 45 minutes to get to grandma's house, that's your total distance, whatever it is to grandma's house, divided by your total time, you could get your average velocity, your average speed. But at any one point, you could be sitting still. You might have to stop at a red light, or you might be going really fast, or you might be going slow. So you have your instantaneous velocity, what your speed is at that moment, and then you have your average speed. Now, in physics, we use the Greek letter delta, which is just a triangle. It's named after the Nile Delta, if what I've heard is true. So it's just a triangle, and it is the Greek letter delta, and it means change or difference. So if we're getting our average speed, we do delta t divided by delta d divided by delta t, which is the total change in it. And then instantaneous would be just at that instant. And that's like if the police get you with the radar gun. That's your instantaneous speed. They don't care that you were obeying the law 4 miles back. They want to know, what are you doing right now? All right, so those formulas are in your book, so let's do a problem. So how I want you to do these problems is I want you to, on every single one of the example problems in the book, I want you to do it on your calculator and make sure you can get the answer. So don't just watch me do it. What physics is it's word problems. And so we just got to get rid of the words and make it a math problem, and that's what we do. So if you love math and you love word problems, you're going to love physics, because that's all physics is a bunch of math and word problems. So our first example problem is in your book on page 45, and it says, in the 1988 Summer Olympics, Flojo won the 100-meter race. So do we care about any of those as far as our math goes? No. The only thing we care about is once we get to a number. And so we were given 100 meters, so that's a distance. So I don't worry about anything else, and I just write down the distance is 100 meters. And then it tells us that she won it in 10.54 seconds. Well, that's a time. So I write time equals 10.54 seconds. And I always list my knowns and unknowns over on this side. And then it asks me to, it says find her average velocity. So velocity equals what? Always write down what I'm looking for, because I have been known to be too enthusiastic about a problem. I know that's hard to believe. And I'll just run off solving for something else other than what they asked for. And I'll do it right. And I'm all happy about it. And it's wrong because I didn't answer the question. So I list my, what I call knowns and unknowns over here. Then I think, is there a formula that I can use to solve this problem? And there is. Speed, but we're going to say velocity because they like it in this book, equals distance over time. So write your formula down in its famous way, and then you sing the song Substitute by The Who. It's before my time and yours, but this is the song we sing. And we're going to substitute in the numbers that we have into the formula. So for I leave. V is my unknown, the velocity. And for distance, I put 100. And for time, I put 10.54. And it's good to go ahead and write your units in there too, because then you can do the math on the units and make sure you have the right answer. So 100 divided by 10.54 is 9.488 meters per second. Ta-da! And we would round that off. I would round that off to significant figures if we needed to. Remember, we talked about that before. Then they said to convert it to kilometers per hour. So whenever you do a conversion, you start with writing what you know. And your what you know is the number that you're starting off with that you want to convert. So it's 9.488 meters. And I write meters in the numerator and seconds in the denominator, because seconds is after a slash, it's in the denominator. And they want us to change it to kilometers per hour. So I want to change meters to kilometers. So I put meters down here in the denominator, and I put kilometers on top. And the relationship is that there are 1,000 meters in 1 kilometer. And now I'm cancel out meters, and I'm left with kilometers per second. But they didn't want kilometers per second. They want kilometers per hour. So now I have to change seconds to hours. So I write seconds on top and hours on bottom. And I don't know the relationship. I'm going to have to do it worse than that. Sorry, I'm going to have to do better. I'm going to put seconds on top and minutes on bottom, because there's 60 seconds in 1 minute. And now I'm going to have to go again, put 60 minutes on top and hours on bottom. So now seconds cancel out, minutes cancel out, and I'm left with kilometers per hour. Any number on top you multiply, so I'm going to multiply 9.488 times 60 times 60. And then I'm going to say enter in my calculator. And then any number on bottom you divide. And so then I'll say divided by 1,000. Any number that's 1, you don't have to bother doing anything for. So it's just going to be 9.488 times 60 times 60. And then enter, and then divided by 1,000. And it should give you the right answer, which is 34.16 kilometers per hour. That's written messy, but that's what that is. You can pause it if I'm going too fast once I hold it up. All right, so that's just a real simple speed problem. So our second thing is says finding displacement from velocity and time. So that one was easy because it was just a simple division. But sometimes we have formulas where it doesn't fill in so nicely. So let's do the second example problem. It's the same problem, it's just we're going to have to remember our algebra rules to be able to do it. Okay, so here's our second problem. It says, it's on page 46. It says a high-speed train travels from Paris to Lyons, Lyons, I don't know. I'm probably saying that in perfect French. At an average velocity, so my velocity equals 227 kilometers per hour. So none of those words are important till we get to the number. The velocity is 227 kilometers per hour. The trip takes 2 hours, so that's the next thing that's important. And how far is Lyons from Paris? So I have gotten rid of all of those words, and I've just got now knowns and unknowns. Excuse me. So now I write my formula. Velocity equals distance over time. Now what do? I sing, substitute, and I'm going to substitute it in. So 227 equals D over 2. So now I've written my formula and I substituted it in. So now I ask myself, why is D not alone? Well, it's being divided by a 2. So what's the opposite of divided by 2? Multiply by 2. And what I do to one side, I do to the other, because you're allowed to do anything you want in math as long as you do it to both sides of the equals. And what I wanted to do was multiply by 2 so I could cancel them out and D would be by itself. So now I just have to multiply 227 times 2 and I have the answer. So the distance is equal to 454, and that would be kilometers. Kilometers. Ta-da! Okay, so let's go on and look at some more ideas. So constant velocity is something that's not speeding up, slowing down, or changing directions. And there's a lab that you could do with that. Have we passed it yet? Not yet. We in a couple of pages, but we were not able to do it last year when I taught this because I had a constant speed car. It was this little truck. It was like a jacked up truck where it's way high up on its wheels. I got for $4 at KB Toys. You know, it was a long time ago because KB Toys has been out of business a long time. But one of those bad kids I used to teach stole it. They stole my truck and they stole my coat. I had a brand new coat from LL Bean, and this kid stole my coat. I learned to lock stuff up if I wanted to keep it. I left my coat on my teacher's chair, just like, you know, I took it off and it was on the back of the chair. Came back and my coat was gone. I kept looking to see if some kid was wearing it. I was going to be like, you got my coat. But they had the sense not to wear it back to school. So never saw my coat or my truck again. Anyway, it was a toy truck though. But they're hard to get because like you have pull back and go cars, but they're not constant speed. They're speeding up. Or you have those ones that bounce off of the wall and flip over and stuff, and they're not constant speed either. They speed up and slow down, and they don't go in a straight line. So it's really been hard. I've been on a search for a constant speed car. And last year, one of my students brought a remote controlled car that was like this big that he had got like at Walmart, and it did pretty good. It did. You had to let it get going a little bit before you started measuring it because it definitely had a acceleration period. But once it hit its maximum acceleration, we were able to do the lab. So anyway, if you've got a constant speed car, like a little battery car that you turn it on, it just goes one speed in a straight line. It's a nice lab to do, and I enjoy it because why do I like it? Because it makes a good graph. The math teacher in me likes the good graph. So anyway, so look in your book on page 48, and you see a position versus time graph. So it looks like this, with time going this way and your position changing this way. The graph will look like that. Okay, now, and you can figure out the slope of this graph by your slope is, if you remember this from algebra, it is the change in y over the change in x. It's rise over run. So, and if you had me, I gave you, I think, a slope program for your TI-84 graphing calculator. So they're out there too, which are useful. So take a look at those ideas in your book. And there's the constant speed lab. It's on page 50. If you've got a card, then I'll assign it. But if you don't have one, you don't have one. It is what it is, as Bone Hampton would say. All right. Now then, so on page 51, this is what I told you about how they will say velocity instead of speed, because they say if it's positive, then that's its direction. And if it's negative, you're going back the other way, and that's its direction. And that's why it is a velocity and not a speed. If you look on page 52, they have a graph that is showing, let's see if I can show this to you. It's right here. See where my fingers are pointing? And it's showing what is happening as something is moving along. So look over there at that graph. And it starts off that they head off for the first 10 seconds 200 meters away. And then they stop and time goes on, but they are not going any distance. They're going no speed, no meters per second. And then they go back to where they started from. And so then it's negative. And then they go back like to home base again. You can imagine it like that. And you can calculate each part of the journey. Let me find my eraser, and I think I'm going to write it, and then I am going to show it to you because this is going to be otherwise irritating. So from A to B, they go 200 meters in 10 seconds. So their speed is 20 meters per second. Then from B to C, it doesn't go anywhere. It's 0. It's flat. So no meters per second. From C to D, it's going back the way they came, so it's negative 50, and it took them 5 seconds to do it, so it's negative 10 meters per second. And then from D to E, they go in that same negative